Hello, it's Keith here, and this is lesson 3 of my PowerPC assembly programming tutorials. Now we're going to be looking at conditions, comparisons, and also related to that, branches today. These are actually quite complex, as are a lot of things to be honest, on the PowerPC. However, like a lot of those things, we can actually make them quite simple because we have some pseudo operations that the assemblers provide for us that make actually the complex commands irrelevant. We can simply use the very basic ones and they do all of the complexities for us. We're going to be looking at both today. We're going to look at the ones that I would recommend you use, but we're also going to not hide the truth of the fact and what is actually going on underneath the hood, so to speak. Now, one thing I would point out, especially true of today's lesson, is while I would recommend you download the tutorials and the build scripts and try these out yourself at home or with all of the lessons, this one is going to be especially important because while I'm going to show you the commands being run with some parameters, I'm not going to show you every possible comparison you could do or every possible branching command you could do. There's a wide, enormous variety of them. I'm only going to give you the very basics. I'm hoping you're going to try this out yourself because in general, if you're not going to, then you're only going to really get a brief overview of this. You know, you're going to have to try these things out yourself one day if you're going to write your own programs. And as I say, it's going to be especially true today when we're only going to look at a handful of the branch commands. Anyway, let's go over to our code. Let's check it out. Okay, so today is lesson 3, so we're looking at the lesson3.asm file today, and as with all of my tutorials, we have a series of branches at the top. All we need to do is enable one of them. The first one we're going to run is the compares branch. Okay, well, let's have a look at what we've got today. Well, the first thing we're going to have to do is we're going to have to discuss the compare command, and this is where, as I say, things immediately get just a little bit strange, really. I would say the compare command on the PowerPC is a little bit different to the other ones. Now, the compare command takes two numeric values and a pair of registers. Now, on most systems, pair of registers, completely understandable. You're comparing two values to each other. But what's these other two numbers? Well, the second number is actually pretty irrelevant in this case. The second number is a 0 if we're doing a 32-bit compare, or a 1 if we're doing a 64-bit compare. And actually, the 64-bit compares don't work on this processor that I'm emulating today, so that won't do anything, and we really shouldn't use it at all. But anyway, so that second value would always be 0 if we're doing 32-bit comparisons. But that other value, well, what is that? Well, that is actually which one of the fields within the flags register we're actually looking at. The condition register, you see, is an entire 32-bit register, but each condition field is only 4 bits. So we have a variety of potential options that we can set when we do our comparison. Now, the default would be CR0, and this is in the IBM bits 0 to 3, which are actually at the top of the register. This would be bits 31 to 28 in the bit numbering of any other system, but as I say, IBM bits reverse. Bit 0 is the top bit, and bit 31 is the least significant bit, which is backwards to my way of thinking. Anyway, the point I'm making is that the 32-bit register has a total of 8 different CR fields, the condition register fields. So these are 0 to 7. And we would specify which one of these we are setting with our compare command with that first value. So 7 would specify that we are setting CR7. We are here just specifying them as a simple number, but for clarity, I would actually prefer to use CR2. That is exactly the same as specifying the number 2. And as I say, the following value after that, the 0 there or the 1 there, that is whether we are working in 32 bits, a 0, or 64 bits, a 1. But as I say, that 1 value there will actually have no purpose here. So let's just fire up our assembler here and let's see what actually happens here. So what we've basically done here is we've set a variety of the condition registers fields, 7, 6, 5, 4, and 2 here. And you can see there, 7, 6, 5, 4, and 2 there all have the value 8 as a result of this comparison. Now, if we had done a different comparison, obviously we'd get a different value. And if we had used a different field here, if I specify CR1 here instead, I've specified it just as a 1 here, you can see now that the value 8 has moved to field 1 there. Each one is conveniently a nibble in that CR field there. So that is the full compare command. But as I said, I would suggest actually you probably don't want to use these. It's much easier to use the simplified versions, which are CMPW and CMPLW. Now we're going to use CMPLW first. This is compare logical word. Now logical means unsigned, so we're comparing unsigned numbers here. And we're going to be using the registers R3 and R4 for our comparison as a test. So we've got some values here, loading R3 with 100, 100 in decimal, and 110 in R4 there. And so we're comparing R3 to R4. Okay, now we're showing the contents of the registers to the screen here for convenience in our testing, but then what we're going to do is we're going to use a variety of branches. So we've got a branch if greater than here, or a branch if less than, and we are going to use these two. And these are going to basically use the comparison we did up here, our unsigned comparison, and if R3 is greater than R4, then this branch greater than will occur. If R3 is less than R4, this branch less than will occur. Now, where do these go? Well, we've just got some simple code down here for showing the result of the branch to the screen. We're just showing a character to the screen. And as I say, this is where I would really hope you would consider downloading this and trying it out at home, because the idea is that we're going to put various values in R3 and R4 and try them out and just see which of the branches occur. But of course, you may want to try different kinds of branches. We have a whole myriad of branches. We're not going to try all of them. We've got a whole variety here. But as I say, we're just going to try a very small number of them, and we're just going to try a very small number of values here. So let's just run our example. Let's see what happens. Well, we did our unsigned compare here. We've got our values in R3 and R4 here. And in this case, R3 is less than R4. So the branch if less than occurred to show LT, because R3 was less than R4 when we did our compare. And that routine just simply shows that less than character there to the screen. Okay, so that's the branch to less than has occurred because of the condition we did here. So there we go. Now, what happens if we give R4 a different value? Let's give it a value that is actually lower than R3. So now it's got a value of 90. Let's run it again. Okay. Well, this time the branch if less than didn't occur. It was the branch greater than that occurred. So we branched to show GT. We showed that greater than symbol because, of course, now R3 has got a value of 64 and R4 has got a value of 5A. So it was the greater than branch that occurred there. So that's why that's happened. Okay, let's try a different value. Let's try a value that you might realize the problem with. We're going to try the value minus 110. So R4 is equal to minus 110 and R3 is equal to 100. Well, it would seem likely when we do our comparison that R3 is going to be greater than R4 because R4 is minus 110 and R3 is a positive number. Well, let's have a look at what happened. Well, it didn't actually work. The branch to less than occurred, which would imply that R3 is less than R4, but R4 should be lower because it's minus. What went wrong? Well, this is, of course, signed numbers. If you look at our hexadecimal values here, there's 64 in R3, which is a smallish number, and R4 contains this unsigned huge number, but a negative number if we were working in signed numbers. Now, on some processors, it's the branches that would be the signed or unsigned part of the equation, but in this case, it's the compare command. We did compare logical word. The logical means unsigned. Our numbers signed, and now we need to be working with signed numbers, and so we don't want to use CMP-LW, we want to use compare CMP-W, and this is for signed numbers. So if we run again here when we're using the proper compare command, well, you can see now that our values, of course, in the registers are the same, but the result now is that we've got a greater than. So there we go. So that's how important it is that we use the correct branch for our comparisons. Okay. Well, let's try something else now. Let's just try putting both values with the same value here. So we're going to give R4 the value 100 and R3 the value 100. And it's going to be fine to still use a signed comparison. Won't make any difference with these values. And if we just run again. So this time neither greater than or less than branched. It was the branch equals down here. And so we showed the equals sign here. Now, you might notice that there's a difference between these, and it's those pluses and minuses. What do they mean? Well, these are actually entirely optional. We can take them out and we can run, and it will run apparently to us in exactly the same way. So we get the same result, we can take them out. So why bother with that extra one character of typing? Well, this is all to do with how the processor actually works as efficiently as possible. On these modern processors like the PowerPC, the instructions are actually being loaded before they're executed, and so the processor is always looking ahead a few instructions and starting to read in the data to work on it, and this is known as the processor's pipeline. So this command's being run, this command's being processed, this command's being read out of memory, and so the pipeline is always working a bit ahead, and this causes a problem when we have a branch, because maybe the processor is actually loaded in data that is never going to be needed, and that's not just meaning we've loaded the wrong stuff, we then need to flush that out and load new stuff back in, and that all adds time to the actual processor's job. So what we want to do is we want to tell the processor whether we think that the branch is going to occur, in which case, don't load the stuff after the branch, load the stuff at the destination of the branch, or if it's not going to occur, in which case just forget about the branch, you probably won't need it, load the stuff that's coming next. And that's what these do. The plus means we think that this branch is going to occur. We're feeling positive that the branch will occur. If the minus means we're feeling negative, we don't think that branch is likely to occur. And this tells the processor what it should be doing when it gets to this command. That's why they're optional. You don't need to tell the processor. It'll just do whatever it can. But if we tell it, then that allows it to work a little bit more efficiently. If you're just a beginner, just having a bit of fun, you don't need to worry about it, of course. This is more about if you're trying to write very optimized code. So I'm just mentioning them here. I don't think there's something a beginner, a hobbyist is going to need to worry about, but I wanted to be clear as what these were. Now, we've been looking at these very nice looking commands, BGT, branch greater than, BLT, branch less than. All very nice and clear, but once again, these aren't actually the commands that are really being executed. These are pseudo operations. These are nice looking things that make things easy for us, but actually there are alternative commands that are actually being run under the hood, so to speak. Now, when we do these commands, we're actually going to be using these branch conditional commands here, and these again take a couple of weird parameters. Now, the first of these is a bit mask, which is actually defining what actually occurs when we do the comparison. The next one is a bit number within the condition register. Now, once again, these bit numbers are in IBM bit code, and so we've got 0, 1, 2, and 3 here. Now, bit 1 is the greater than comparison here, and bit 0 is the less than, and as I say, these the IBM bit 0 and 1. And so these are the entry within the 4 bits of our condition register that we actually want to use when we're doing our comparison. So that's the second parameter. The first parameter is even weirder. It's a binary code, and this binary code is simply one of these entries within this list here. Now, if we just go over to our other screen again, it'll be a little bit clearer than on that screen. So here are the various bit options here, and then these are actually doing various things. Now, they could be as simple as branching if the condition is false, or branching if the condition is true. There's even a branch always, but we have these weird ones like decrement the count register, and then branch, and so on and so forth. So we've got this really long list of various complexities, and we've also got the Y bit there, which is actually whether we're expecting the condition to be true or not. So that is that's the branch prediction that we have the option of using. So here what we've done is we've basically got a branch if condition is true here, and we are using the bits 1 for the greater than field in the condition register and 0 for the less than field in the condition register. So that's how we are effectively doing the same as these commands here, just with a lot of extra code here. Now, if you prefer, you can actually sort of simplify these a little bit, and you can have branch if true, and then have the condition code GT for greater than or LT for less than. That is another acceptable syntax. Again, another way of using these kind of commands. But as I say, I think for general purposes, while I think it's worth knowing this is how things work under the hood, so to speak, I think in most cases you're going to want to use the simplified pseudo operations. And as I said before, if you go to my website and you download my cheat sheets, a printable cheat sheet collection you can download for free, I do have a list in that of all of the pseudo operations that are available. So if we go over to my book screen here, you can see here you do have a list of all of the possible options there that do allow for the very strange things like branching to the link register in the CTR. There's a lot of things that I think as a beginner you're not going to want to worry about, but they do exist, and so I just need to make you aware of that so you are not underinformed. Okay, so that's a few simple comparisons. As I say, you're welcome to download these examples and try them out yourself with other values and other branch types to make sure you understand things as much as you want. Now, what we're going to do now is just look at one of these more strange branch options, and we're going to look at the BLTLR command here. Now, you'll notice there's no label here, and that's because we're going to branch if less than to the register link register. Now, this of course is typically the return address. This is set automatically by the branch and link command, and so what we've got here is actually a return if less than command, which is something the Z80 has, but most of the processors don't actually have that kind of thing. So I thought it was quite interesting to see it here. So what we're going to do here is we are basically going to have a branch here. What we're going to do is we're going to load in some test values here, and then we are going to do a comparison here, and we'll just simplify this down a bit. We've got too much stuff here. So let's run this and let's see what happens with this compare to command here. Okay, now what's going to happen here is we're basically going to show the letter Y here at the end of our code here, but then we've got this branch and link to this link condition routine here. This is going to do a comparison. It's going to set the registers accordingly, and then if the register R3 is less than the register R4, we're going to jump to the link register, which is effectively a return. So this part of the code in that case would never occur. So that's what's effectively happened here. So this N has never occurred. We returned back to here and we showed the Y to the screen. And that's because R3 was less than R4. Well, what if R3 is greater than R4, like with these values here? Let's run it again. Well, in this case, we've branched and linked to the link condition here. This is this label here. We've done our comparison here, but this time the R3 is not less than R4, so the return to link register hasn't occurred. We've shown a character N to the screen, and then we've actually branched to our infinite loop, so the return has never occurred in this case. That has shown the N to the screen. As I say, this is one that's potentially useful in some cases because, as I say, most processors don't have a kind of return command, a branch and return command, but this can be used as one. The only problem I can foresee with this is if you're nesting your subroutines and things, you're probably going to want to push the link register onto the stack or something, and that's going to mean that it's not actually present for this return. And of course, you could also, if in some cases, maybe use this as a jump to subroutine by having the subroutine you may want to call within the link register. There's going to be a lot of potential here, and in most cases, again, I think this is probably a little more confusing than you probably want to make things. You probably just want to keep things simple and just have simple branch commands, and then you have your returns and things as normal commands. But again, it was impressive to see a command with a lot of potential flexibility on the PowerPC, so I just wanted to mention it existed, even though, as I say, it's possibly a bit too much for you in most cases. Now, here we're dealing with various entries within the condition register. So all of these default commands will always just use CR0 where we're not specifying something else. But I think it's going to be a good time to take a look at the condition register and learn how we can work with the various bits within that condition register and do other things with them. Now, the first thing we may want to do with a condition register is actually take its value and store it in another register. So we may want to move from the condition register to another register, maybe R3 for example, and that's what we've done here. So we've moved the value from CR into R3. You can see here at the top here, CR equals 2 and 8, 2 at the top and 8 at the bottom, and you can see R3 contains the same value because we've moved it. Now, we've actually seen that before. We did that before when we were backing up the condition register, moving it into R0 and then pushing R0 onto the stack, because we can't push the condition register onto the stack, but maybe we will want to when we're having subroutines that change things. So that's one thing you may want to do. Now, another thing you may want to do is move values back into the condition register. So we can back up the condition register with MFCR. We can restore, if you will, the condition register with MTCR. Although actually here we've loaded a test value into R0, and then we're going to transfer only some of that to the condition register. You see, MTCRF means move to condition register fields. There's actually no MTCR. We have to specify the fields we want to update. We back all of it up in one go here, but we restore it optionally in different parts. Now a bit of 1 here specifies that the matching condition register field will be changed, and a bit 0 means it will not. And you can see that the top bit 7 there is a 0. Bit 7, I apologize, that's bit 7 in conventional numbering. In IBM bits that would be bit 0, and that means condition register field 0 is going to be unchanged here. Because all the other bits are 1, we are going to change all of the other condition register fields, and they will take the values in this test value here in R0. So you can see here R0 contains FEDC BA87 here, but when we've transferred it, we didn't change condition register field 0 there, so that means that the bottom bit has been left as a 2 there. Now we can just confirm that that's what's really happened here by simply adding some more zeros into our mask here. So here we are now leaving all of the higher condition registers fields 4, 5, 6 and 7 here unchanged, and so you can see here they are left unchanged as well, and now we've only changed 3 of them. So that's how that works. Now, if you want to change all of them, for example, if you're restoring the condition register from the stack via R0, you would just want a value of 255 with all of the bits in that mask as 1. But maybe you want to do something else, and so that's how you can do it. So that's how we can move from a register to the condition register, but we can actually move within the condition register itself. So maybe we've been doing something with condition register field 0, and maybe we're going to need that later again for another comparison or another branch. But we need to use CR0 for something else for a while. What can we do there? Well, the mcrf command will move between condition register fields. So here we're specifying 7 and 6. So the destination is on the left of the comma and the source is on the right. So this is copying the value from field 6 to field 7. We've specified them numerically first time, but I'm using the clearer CR5 and CR4 the second time. But you can see here that here's the condition register before those copies, and after them you can see that condition register 7 and condition register 5 have been copied from the other register as specified by these commands here. So that's how we can move bits of the condition register around. Now there are some quite interesting logical operations that we can do. We can actually perform logical operations between 2 condition register fields here. So here we are using CR AND here, and we are basically going to specify that we're going to AND bit 28 with bit 24, and we're going to store the result in bit 0 here. Now, why would you want to do this? I'm not honestly entirely sure. I couldn't exactly think of a particular time that I would need to do this, but there's a wide variety of these options, so I'm sure there is a very good purpose you would want them for that I can't think of. So there they are. I will let you know about them, and you're welcome to come up with a great use for them that is far smarter than I am. Anyway, that's those commands. Now the other thing that's relating to the condition registers is the XER register. Now the XER register has a variety of bits that do a variety of things. The bottom bits are a byte count, a byte compare value, a bunch of unused values, but then the top 3 bits, or the bits 0 to 2, as they would be in IBM numbering, top bits in conventional numbering, these are actually basically various kinds of flag, if you will, a carry, an overflow, and a summary overflow, which is an overflow that never clears with subsequent commands. Now, we might want to use those for some kind of comparison, and so while we can't access the XER in the same way as the condition register, generally speaking, what we can do is we can transfer the XER register's top 4 bits, including 1 0 bit, into one of the condition register fields. And that's what we're going to do here. So what we're going to do is we're going to transfer the value 7 into the XER, into those top bits, just as a test value, so that we can easily see them and confirm they've been transferred. And then we're going to move to the condition register field, and we're going to use field 7. Now this command actually clears the XER bits that we've actually transferred. It's a full-on shift. It's taken them away. So the XER bits will be cleared by this command. And so once we've run this, we can see that the XER, the top bits, have now been zeroed. In fact, all of the bits are 0. But you can see that the last nibble of the condition register now contains the value 7. Well, maybe we're not convinced that really happened. Let's try a different value. So let's load the value 6 in this time, and let's run that again. Well, this time you will see that the condition register, that the least significant nibble there, contains a value of 6. And of course, if we just disabled this command, we can see that that the value 6 has been loaded into the XCR by these commands here. So that's how we can work with the condition register and shift the various values around its fields. It's very powerful, as I say. It's a little bit difficult, the extra complexity, but it's very impressive, the extra functionality that really you know, multiple flag options for comparisons and things isn't something you see really in other processors. So again, difficult but worth mentioning. So what we're going to do next is we're going to learn how we can do a simple loop using the count register. Okay, so the count register is a special register. It's CTR. We can't access it directly, but what we're going to do here is we're going to load a value 4 into R4 and then shift that into the CTR. Now you can see here that the R4 register contains the value 4 here, and in this dump here you can see that that's been transferred to the CTR, which also contains the value 4. That's MTSPR for moving to a special purpose register. We can move from a special purpose register. We're moving from CTR into R5 here. And again, you can see that has occurred just here. So that's how we can set the CTR register. But what can we do with it? Well, the simple thing we can do with it is we can use it as a loop. So the BDNZ command will branch and decrement the CTR while it's non-zero. And so while it's non-zero, we'll jump back to loop test here. So loop test is here. We're just going to simply repeatedly add 1 to R3 just so we can see how many times the loop occurred. So each time we're going to show R3 to the screen here. So the first time that the loop occurred, R3 will have contained the value 1, and you can see that here. Then the CTR register will be decremented and the loop will occur again. So we see 2, 3, and then finally 4, and then after that the CTR will have reached 0, and that loop has ended there. So that's what BDNZ does. I think the most accurate description of this would be branch after decrement if not 0, because the decrement occurs and then the branch will occur if the condition is true. So until the CTR register reaches 0, we're going to branch back to loop test there. Now that's a simple version that just continues until the CTR reaches 0. However, there is an even more complex one which is going to have a condition. So what we're going to do is we're going to actually have 2 ways that this loop can end. The first one is if the CTR, which contains the value 4 again, reaches 0. The second one is if our condition occurs as performed by a comparison here. So we're going to compare R3 to 2, and we're also going to break out of this loop if the condition is equal. So if R3 equals 2, the loop will end. Well, let's see what happened then. So we've done the exact same process again, and this time the loop has only occurred twice because, of course, R3 reached that secondary condition of 2, and so the branch condition that the CTR reached 0 never occurred. The comparison here set the flags, and that equal condition occurred instead. Now, of course, if we set a condition that would never occur, for example, if we change this so that the comparison was seeing if R3 reached 200, which of course it never will, because the loop is still being restricted by the CTR, which has a value of 4. So this time R3 only reached the value of 4 here because the comparison never reached a true condition, but this was still being limited by the fact that the CTR had to be non-zero, and the CTR reached 0 after 4 iterations there. So again, it's another case where I would probably just stick to using the simple BDNZ command, but you do have these options to put in a secondary condition that can cause the loop to end. And there we go. So that's all we're going to be covering this time. We're going to be covering other commands next time. We're going to be looking at logical operations and bit shifting. They are very important things in all assembly languages, and of course the PowerPC has them as well. As I say, go to my website, download the source codes and build scripts, and you're welcome to have a go with these, and hopefully you'll have some fun with them. Anyway, I hope you enjoyed what you've seen today. Thanks for watching, and goodbye.